So today we'll be discussing the paper DreamBooth by folks from Google Research and Boston University. Uh, so what is this paper about? This paper is very similar to another paper I discussed, textual inversion, in that you take a pre-trained text-to-image diffusion model like Imagen or Stable Diffusion. Then you give a few input images of a subject and you try to render new images of that subject in some new settings given by prompt. So uh, if you give like 4 or 5 photos of typically 3 to 5 photos of say a dog of this particular dog, and then you can generate images of this particular dog in new settings like in the Acropolis, swimming, sleeping in a bucket, getting a haircut. So yeah, it is pretty cool. Uh, why am I covering it when I already covered texture inversion? First, because it is one of the popular approaches along with textual inversion. They have a lot of similarities, but some differences. In that, texture inversion did not change the model, whereas this approach fine-tunes the model. So that makes them fundamentally different because this approach can, since it is fine tuning, since textual inversion was not fine tuning the model, it could not create anything uh, newer than what it was already trained on. Like it could just interpolate. Uh, you couldn't teach it a totally different concept. In this case, since you're fine tuning the model, you can actually create, probably, I don't know, but you can probably uh, train teach it some new concept. Secondly, they also the main baseline that they compare against is textual inversion only, and they claim that their approach is better able to preserve this exact subject than textual inversion. Like rendering this exactly similar dog here, they are better at it than textual inversion. Textual inversion sort of captures the whole concept in a way. It does not. Uh, it does not retain the features of this particular subject. It will learn that okay, this represents the concept of a dog which looks somewhat like this, and it will generate images of dogs which look somewhat like this dog, but not exactly like this dog. Whereas in DreamBooth, you can create renditions of this like exact same dog in different scenarios. So that is a bigger difference between the two approaches. Right. So how do they do this? Well, we'll get to that in a while. But first, let's see the motivation of the approach. So they say that existing large text-to-image models are great. They're awesome. You can create a lot of good images out of it using text. And one of the reasons why they're so awesome is because they have a very strong semantic prior learned from a large collection of image and caption. So such a prior enables them to bind, say, the word dog to various instances of a dog that can appear in different poses and contexts. So they say the meaning is that since it was trained on such a huge data set, the model has a really good understanding of, say, what a dog means. So it can actually render the dog in different contexts and different poses because it was trained on a huge data set where the caption contained the word dog and the image had the dog in a certain context according to the prompt. However, while it is great, they lack the ability to mimic the appearance of subjects in a different reference set and synthesize novel renditions of the same subject in different contexts. So they basically say that it is hard to give a few examples to these models and ask them to create new renditions of the same subject in that different context. So, giving a few images of this corgi, I think it's a corgi. Is it a corgi? It's probably a corgi. It's a diffusion paper. They love corgis somehow. So, of this particular corgi, and the reason for that is that they say that the expressiveness of their output domain is limited. So how are you getting the output in these models? You are getting the output using text. You are giving text input to the model and you're giving a caption to the model and you're getting images. So they say that even the most detailed textual descriptions of an object may yield instances with different appearance. So if you want to create an image of this corgi, and if you're just using text, there's it is very hard to specify in text how exactly this corgi looks like. You can say it is a corgi, it is cute, and it is like on an orange background, but it will generate a random corgi. It won't generate this particular corgi, and it is very hard for you to specify in text how exactly to get this particular corgi. So yeah, that is something, and that is why they instead want to learn much similar to textual inversion. They actually learn a new token or a new embedding representing this particular corgi. So they say that formally, given a few images of the subject, their objective is to implant the subject into the output domain of the model so that it can be synthesized using a unique identifier. So same as textual inversion, they want to learn a new identifier for this particular subject. But whereas in textual inversion we were learning the general concept, in this case we want to learn the subject, like the exact way how it looks like, not just the concept. An interesting thing here is that while in textual inversion they froze the model, the pretrained model, in this case they are fine-tuning the text to image model they have, and they're fine-tuning it with a special prompt. So for that corgi image, they'll give a prompt saying a V dog. So V is here the special identifier which you want to learn, and dog is the class of the subject. So in this case, they are supplementing the caption with the class of the subject. So since that subject is a dog, you are giving the word dog in the caption. And they're doing this to use the prior knowledge the model has about, say, what a dog is. So this dog will allow the model to leverage its existing knowledge of what a dog is, and the special token V would actually represent the particular dog that we want to generate. And herein lies a problem I have with the paper. Like, since we are relying on a existing class, this might not work if we want to generate images of a concept which is not there in the classes, or like if we don't have a proper word for it. If I create something new which I don't know what to even call, it might be hard to like create it by this model. But okay, yeah, that is maybe something which is anyway hard. But yeah, textual inversion might work better in that case. I don't really know, because textual inversion does not fine tune the model. So if we create something which is totally new, it might not be able to generate. But here in this case, we won't have a class for it, so this also might not be able to generate. So yeah, maybe creating something which is completely new is not something that can be done by both of these models due to different reasons, which are actually the same, I think. Then they talk about some regularization losses which they have, which I'll talk about later. So now let's talk about the approach itself. So first they cover text to image diffusion models, which I think I don't really need to cover because I have covered those in my textual inversion video, and I think they're very popular. But in a high level, you have a diffusion model, you give it a text and it outputs an image. So you give it a text saying an image of a corgi, and you will get an image of a corgi. That's the output. I mean the actual image, not the text. You give it a text and it produces image. So for this task, you might think that the natural thing to do is to fine tune the model using the few examples you have. But they say that naively fine tuning can be hard or can be counterproductive, because they have observed that when generative models such as GANs are like fine-tuned in a few short setting, they can overfit and suffer mode collapse and not capture the target distribution sufficiently well. So if you give say 5 examples of this corgi, it might overfit to those 5 examples and just generate images which look like exactly or very similar to the examples you have provided. It might not be able to create diverse outputs, right? And also they say that the old approaches just wanted to capture the distribution and not exactly the subject. So if you give 5 images of a corgi, they might be focusing on capturing the essence of a corgi and like understand how a corgi looks, but not generate the exact same corgi who you gave in the input. So instead, in their case, they do something different. As I said before, they have a special prompt, which is like for each image, they have a identifier and a class noun. So the identifier is the the new token we're learning, and the class noun is the class of the image, class of the subject basically, and it is a course class. So like for a corgi, you might use something like a dog. You wouldn't say that it's a corgi. You would just say identifier dog. So it is a course class. It's not very granular, and they say that this can be either provided by the user or obtained using a simple classifier. And the reason to use this is so that the model can leverage its existing understanding of what like a dog is, or and then use. So this identifier can be used to incorporate the existing knowledge the model has about dogs, and this identifier can be used to encapsulate the knowledge about that specific subject, that specific dog, right? So this is what they say. We want to leverage the model's prior of the specific class and entangle it with the embedding of our unique identifier. So we can leverage the visual prior to generate new poses and articulations of the subject in different contexts. Then they talk about how they generate these unique identifiers. It's just an implementation details. I'll just skip it. More importantly, they have a class-specific prior preservation loss. So what is this? Uh, they talk about something called language drift. So they say that it has been observed that when you fine-tune language models on a language model which has been pre-trained on a very large text corpus, when you fine-tune it on a specific task, it forgets stuff. It loses syntactic and semantic knowledge. So this was alluded to in the textual inversion paper also, that when you fine-tune these large language models on a specific task, they suffer from catastrophic forgetting. They forget their old knowledge, and they say that they observed that diffusion models also suffer from the similar problem, where the model forgets to generate subjects of the same class as the target subject. So if you're fine-tuning it to if you're fine-tuning it by giving it 5 images of a corgi and you're saying identifier dog looks like this, then it might forget what a dog looks like. Actually, it might just start thinking like every dog looks like that corgi only. So this is the drift that they want to reduce. And another problem is reduced diversity. And what they observe is that when you like normally these models are very diverse, they can generate very diverse outputs, but when you fine tune on a few examples, the model might overfit to the particular cases you have given, and it might lose its diversity. And they say that they do observe that this is the case, and especially when the model is trained for very long. To fix these issues, they impose a class-specific prior preservation loss. And what they do here is that it is probably best seen in this diagram. So like they have a frozen model. So before fine tuning, they freeze, like they have a pre-trained model which they're fine tuning. So they have a set of weights which are frozen, so which are not fine tuned, and a set of weights which are represented in red, and a set of weights which are fine tuning. So these yellow weights. So actually both of these weights represent the same thing. Uh, this is the process which they specified, that they will give something like a beat dog and ask the model to generate the given images. So this is how the model is being trained without the regularization, is that you give these special prompts and you ask the model to reconstruct the image which were given in the input sample. However, as a regularization, they remove this identifier. So you remove this identifier and you just get a dog and you want the model, like given the same noise, you want the model to give the same outputs before and after fine tuning. So the model's prediction for the prompt without the unique identifier should be same before and after fine tuning. And this is sort of like a regularizer that if we don't have that prompt and say if we don't have that unique identifier, if we just have a dog as the input, the model's output before fine tuning and after fine tuning should be the same. And this allows the model to not forget the old prior it had about that class, its old knowledge about what a dog looks like. So if you have this regularization loss, then the model will remember what a dog looks like, and when you add this extra identifier, it will then change this dog to look like that particular dog you had in the example. So you get to have both things, and you don't forget your old knowledge about, say, what a dog looked like. And they also say that using this regularization, they can train the model for more iterations without like overfitting. So it's good. So this is the main approach that they used. They used Imagen, and they have two models. One uses Imagen and the other uses Stable Diffusion. The Imagen model is supposedly better in this case. And let's go to the experiments now. So now looking at the experiments, they mainly compare with textual inversion, and so you have these input images. This is the output given by DreamBooth, and this is the output given by textual inversion. They say, and it is also very obvious, that DreamBooth performs better in preserving the exact subject, whereas textual inversion actually captures the concept. So it gets sort of the idea of what this is trying to represent, the concept. Okay, this reddish vase, and it is creating images which represent the same concept, but it in this particular case you want not the concept but the exact subject matter to be preserved. So DreamBooth works better. They use Dino embeddings to like do this. Dino is a self-supervised image model, so this is a self-supervised image embedding, and they calculate the Dino embedding similarity between images which are generated and the input images to capture this metric. And they say that uh, DreamBooth is better basically compared to texture inversion by a lot actually in this case. I mean, this does not mean that texture inversion is bad or DreamBooth is better, but for preserving that subject exactly, DreamBooth might be better, and for learning the concept, maybe texture inversion is the preferred approach. I'm not sure. Also, they measure the importance of the prior preservation loss. So they see that without the prior preservation loss, the model's diversity is reducing. So it is forgetting, like it is not able to generate diverse images, it is generating very similar images. And with the prior preservation loss, the model is like generating more diverse images. So the prior preservation loss is important. Also, for the class name used in the prompt, so if you remember, they have a prompt like a identifier and a class noun. They say that that is important, and if you don't provide that class, or if you provide the wrong class, then it messes it up. So they say that if you have an incorrect class, say if you use a can for a backpack, you sometimes like you have an intermingling of sorts. I mean, it gets messed up. And if you don't have a class noun, then it might not even like give meaningful outputs because it could not leverage the prior which that class represents. So just giving a V won't like make it understand that easily how to create this particular teapot. In that case, it needs this teapot thing to give it that prior knowledge of what a teapot looks like. And if you give it a can here, it will get confused and it will be like, why are you asking me to make a can when it is a teapot, and something like that. So yeah, that is that. And then coming to the applications, one of them is recontextualization. So, given the input images, you want to generate images of the subject in new contexts. So, if you have images of this backpack, you can create images of this backpack in like different scenarios, or this teapot in different scenarios. This one is particularly cool because it made it transparent and it worked really well. So, this is very nice. Artistic renditions, you can do like give this images of this dog and ask what it would look like as a Van Gogh painting or a Michelangelo statue. You can generate new views of the image. So given images of a cat, you can ask for its top view, bottom view, back view. You can modify it. You can ask what it would look like, a panda or a lion or a hippo. Then they talk about the limitations, and they do mention quite a few limitations, which is always good to see that they are owning the mistakes. So one of them is that maybe their approach is not sometimes able to accurately generate the prompt, and they say that the reason for this could be a weaker prior, or for this context, or like in general it being a difficult prompt like that subject and that concept might not occur very probably, like with a low probability. So this backpack in the ISS or on the moon, this might not be that easy because it is not that common for a backpack to occur on the moon. So this is a failure case. The second is context appearance entanglement, where the appearance of the subject changes due to the prompted context. So when you ask it to create this backpack in the Bolivian salt flat, it changes its color, or on top of blue fabric, it changes its color, which was not asked for. And this is sort of an entanglement with the prompt, which was not uh, asked for. And they also observe overfitting to the given images when the prompt is similar to the original setting. So one of these images is like sort of a backpack in a forest. So this is just an image, we haven't provided its prompt. But when we ask for this backpack in the forest, it might just simply pick this real image where the backpack was in the forest. So it sometimes overfit to the input image as well. And then they say that some objects are easier to learn than others, like dogs and cats, because they will have a better prior, maybe. And for some objects, they are not able to support as many variations. And in some cases, the fidelity might not be that good, and or there might be some artifacts. So basically, yeah, it's not perfect, but it is. I mean, I like this that they had listed these limitations openly. So yeah, anyway, this was the paper. I think it's a pretty cool paper. It is very popular. People have used it a lot, DreamBooth, along with what is it, texture inversion also. And this is the web page. It is also there on diffusers. So diffusers, Hugging Face also has this, and yeah, it might be somewhere here. Where is this? Oh, Kandinsky came. Nice. Uh, it's training. Yeah, DreamBooth. So it is integrated in diffusers, which is always good. So yeah, that's all for this paper. Thanks for watching.